All right, Chapter 7. Chapter 7 deals with the periodic properties of the elements. We've pretty much done this. Oh, this was Chapter 5 last year. This would have been Chapter 5 last year. It would have been a couple sections in Chapter 5 that we're going to go through, review, and then go through in a little bigger detail than what we did last year. So you may remember talking about like ionization energy, atomic radii, such terms from last year. We're going to go over and a little more in depth from what we did last year in Chapter 7. So when we start talking about the periodic table, let's review real quickly. Remember, Dmitri Mendeleev is the main chemist who gets credit for coming up to how the elements should be grouped in the periodic table. So on the table here, you can kind of see where the elements, what the time in which the elements were discovered. Remember that Dmitri Mendeleev came up with the periodic table. He arranged the periodic table by atomic mass, even though now it's arranged by atomic number. It was pretty close. And he also correctly predicted some elements that didn't exist. So on this slide here, you don't have to necessarily write this slide down. Just know that he predicted elements that had not yet been discovered. And you can kind of show here, made in 1871, Mendeleev correctly predicted the atomic weight of the element that was going to be below silicon. You can see here as you go across the screen, he was darn close on what it would look like for density, for its formulas, for its atomic weight, for everything along the way here. So it's actually pretty spot on. So Mendeleev predicted those based on the characteristics on the periodic table. Now, as you guys know, in the periodic table, there are a bunch of trends that we can establish on the periodic table. So if we look at three things, we're really going to focus on three things in this chapter and all in this section 7.1 today on trends in the periodic table. We're going to talk about size of atoms and ions, we're going to talk about ionization energy, and we're going to talk about electron infinity. Now, effective nuclear charge. All right, so how the heck do we do this? I don't really want you, actually, we're going to skip that for now, so we're going to come back to that later. So don't worry about those last two slides with the effective nuclear charge. We're going to jump right ahead into size of an atom. So the bonding atomic radius is defined as 1/2 the distance between covalently bonded nuclei. Well, what the heck does that look like? Well, it's really just you taking half of the two atoms when they are bonded together. So if you take a quick peek here, here's half of atom 1, here's half of atom 2. The radius, all right, is here to here. That's the atomic radius. It's 1/2 the distance between the bonded nuclei. What we would mean here is if we took the distance from here to here and we took 1/2 of it, it would equal this. That half would equal that half. So that is our definition of atomic radii. You will always be given a chart when we talk about atomic radii. You will be always given a chart to kind of give you the atomic radii. You're not going to have to memorize that. That information will be given when we talk about the size of the elements. So when we talk about atoms and we go across the periodic table, so if you look on the left-hand side of this slide right here, here is the radius of every single atom. So you can kind of see a general trend on the periodic table. The first trend is we go, I'm going to kind of do an arrow. We go big to small, right, going left to right. So atoms on the left side of the periodic table are typically atoms on the left side of the periodic table are typically larger than those on the right side. And you can see kind of that general trend here. Rubidium, potassium, sodium, and the high 1.5s. And we go over to the right side here, and we have argon, krypton, and xenon at 1, 1.1, and 1.3. So why do they increase going left to right? Because it has to do with electron repulsion. All right. So why do they generally decrease uh, left to right? Because it has the kind of electron repulsion. Now the other trend that we have is they increase. They kind of increase as you go down, so or they decrease as you go up. So just kind of an arrow there. And it has increasing radius on the bottom here. Why do they increase as you go down? You're adding more electrons and more neutrons to the individual atoms of each element. Therefore, you're going to increase the size. So, size of the atom. General trend when we talk about size of the atom is going left to right. It decreases, and going bottom to top, it increases, or top to bottom decreases. You can kind of figure out which way you want to learn it. So that's size of atoms. Now, if we talk about ions, ions become very interesting because ions, remember, are different than the actual element. Ions are have a charge. So ionic size depends upon a handful of things. It depends on nuclear charge, it depends on the number of electrons, and it depends on the orbitals in which the electrons reside. So we have a bunch of ions. How do we determine the size of the ion? Well, cations are smaller than their parent atoms. Why? Well, remember, we have calcium. Let's say we have calcium, Ca. We have Ca plus 2. All right, that's the general calcium ion. Plus 2 means that has a charge of positive 2. Therefore, we're removing negative charge. If we're removing electrons, our atom is going to get smaller. So cations are typically smaller than their parent atom, and our parent atom is the original element. So calcium and calcium plus 2, because we are removing electrons, so we're removing the size of the electron. Anions are typically larger than their parent atoms. Now, why is that? Let's use an example like sulfur. We have sulfur as our parent ion, or our parent atom is sulfur. Our ion for sulfur is S minus 2. Minus 2 means that we are adding electrons. If we are adding electrons, we're going to have more repulsion, and the size of our atoms are going to get bigger. All right? So, general rule, cations are smaller than their parent ion, anions are larger than their parent ion. Now, general rule with ions, the size increases as you go down a group or family. So if you go down the periodic table, that's the same trend for the size of atoms. They increase as you go down. Why is that? Because you're adding more electrons to the outer shell and adding more neutrons. So you're adding electrons and neutrons, just like you were with the size of an atom. So, 3 things about ions. Cations are smaller than their parent atom. Anions are larger than their parent atom, and they increase when you're going down. Now, when we talk about ions, we can come across something called an isoelectronic series. Right? Isoelectronic series. Now, what the heck does that mean? Well, if you look at, for example, 3 atoms, it's possible that they all represent the same type of parent ion on the periodic table. And what the heck do I mean by they all can represent the same parent electron on the periodic table? Well, if you look at this, right, and we can compare. Let's have an example. If you pull out your periodic table, I don't have, well, there's a couple here, but I'm going to use a different example. Let's say we have Rb plus 1, Sr plus 2, and Y plus 3. Right? Now, all of those atoms represent the same parent electron. Right? All we've done in Y is remove 3 electrons. In strontium, or Sr, remove 2 electrons, and rubidium, remove 1 electron. So our parent base atom is really going to be argon. All right. It's going to be argon for all three of these, except that rubidium plus 1, we've removed 1 electron from argon. And strontium plus 2, we've removed 2 electrons from argon. And in yttrium, or Y, we've removed 3 electrons from argon. So all three of these have the same base parent atom. So hypothetically, all three of these ions would be the same size. How do we break a tiebreaker when we have a situation like this, which is called isoelectronic series? The ionic size decreases with the increasing nuclear charge, which means that ionic size decreases with increasing nuclear charge. So the largest of our nuclear charge here, +3, would be our smallest atom or ion. Rubidium, since it has the smallest nuclear charge, would be our largest ion, and then strontium is in the middle, would be our medium ion. And we'll do some examples with that in class, and if you have questions on that in class, we'll kind of explain how that size of the atom works. So we have size of atoms and size of ions. That's kind of our first trend that we're going to analyze. The second trend that we're going to analyze is ionization energy. What is ionization energy? It's simply the ability to remove an electron from an atom or ion. Now, there are multiple ionization energies. The first ionization energy is the ability to remove the first electron from an atom or an ion. The second ionization energy is the energy required to remove the second electron. So real quick here, let's review. All alkali metals, group 1, have 1 electron in their outer shell. Is it going to take a lot of energy to remove that 1 electron? Think about this. They want to get rid of that electron. So is it going to take a lot of energy to remove it? No. But those same alkali metals, how about removing a second electron? Once you remove the first electron, you go to a shell of 8. Is it going to be really difficult to remove a second electron from those alkali metals? Yes. So, for example, in alkali metals, the first ionization energy is very high. The second ionization energy is very low. Now, you can see a table here with ionization energy, and it has I1, I2, I3, I4, I5, I6, I7. That's really the ionization energy to remove 1 electron, 2 electrons, the third electron, the fourth electron, the fifth electron, and on and on and on as you go. So you kind of get that. Ionization energy, let's review. What's the general trend on the periodic table? Left to right, it increases. I have that up in the top right corner. Left to right, it increases. Why does it increase? Because it's easier to take the energy away, 1 electron away from alkali metals because it wants to give it away. But it's very difficult to remove it from our halogens. Our halogens, remember, have 7 electrons. Are they going to want to give an electron away? No. So it's very difficult to give the energy increases as we go left to right. It decreases as we go top to bottom. And why? You might remember this analogy from last year. If I have 10 electrons or 1,000,000 electrons, or sorry, not electrons, but if I have $10 or $1,000,000 and somebody asks me for $1, which person should be more likely to give me $1? Hopefully the person with $1,000,000. And the same thing works on the periodic table. If you're asking me for 1 electron and I have 2 electrons or 80 electrons, I'm going to be more prone with 80 electrons to give 1 away than I am with 2. So it's easier to take an electron from elements on the bottom of the table than it is the top if they're in the same group. So that's a general trend. Kind of have that written down with ionization energy. Now, a couple trends. You'd be given this chart, or you'd be given this information as you go. So the trends I already kind of explained. If you want to write these down and pause the video, go ahead. I already explained these next 2 slides on the last slide as you go across the table and as you go down the table. Now, there are 2 exceptions. There are 2 exceptions here in ionization energy. And the first one is that it's harder to take from group 2 than it is group 3. Why would it be harder to take from group 2 than it is group 3? Well, think about group 2. And group 2 is right here. All right. Beryllium, magnesium, calcium, on. If you have an orbital, its s sublevel's completely full. Right. Group 3 over here has a full s sublevel, but then it has one electron to give away. It is actually much easier to take this one electron than it is to break up that full s orbital. Therefore, group 3 atoms have slightly less ionization energy in comparison to group 2 atoms. So that's the first exception on the periodic table. Where is the second one? The second exception comes in groups 5 and group 6. Let's look at group 5 and let's look at group 6. Group 5 is nitrogen, potassium, arsenic. All right. Group 6 is our oxygen, sulfur, selenium, and on down we go. Let's look at the orbital notation for group 5. You're going to have a full s level. Then your p level is going to have one of each electron in it. If we look at our 6, we're going to have up, down, but then we're going to have up, 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 and down. From the electron standpoint, they like, just like when we are comparing 2 and 3, they like having a full orbital. They also like having a full half orbital, which means in group 6, it is much easier to remove one electron here and keep the 3p orbitals half full than it is to remove one electron from the fifth group and have one empty orbital. So it's easier, the energies will slightly drop. It's slightly easier in group 6 to steal an electron than it is in group 5 because they like having the orbitals at least half full. So those are kind of the two what's the word I'm looking for? The two things that don't really follow that trend. They're kind of the trend breakers. So that is kind of the idea there. There are two exceptions to that rule when we talk about ionization energy. The groups 2A versus 3A, and the example that we just got done talking about here, 5A versus 6A. So that's ionization energy. We've talked about size of the atoms. We've talked about ionization energy. Last thing we're going to wrap up is electron affinity. And electron affinity, basically put, is the energy change by adding an electron. So the energy change by adding an electron. That's all you need to know with electron affinity. The energy change by adding an electron. Now, how does that affect things? Well, let's look at trends in electron affinity. In general, electron affinity becomes more exothermic as you go left to right. So in general, it becomes more exothermic as you go left to right. So exothermic, the amount of energy, the energy change by adding an electron. So kind of think about that and how that would work. So electron affinity, there's the general idea. There are no exceptions really in this trend. You can kind of see that the table kind of varies depending on the atom for electron affinity. The reason there's no energy gain in adding electron to noble gases is, are they going to add an electron? No. So there's kind of your exception with the noble gases. Also, the energy gained by adding an electron is going to be great. These really, really want an electron really bad, so you can see why their energies are really high in comparison to the rest of them. The halogens, group 7, really want an electron. So the energy that they give off when they add that electron is very great. Trends in electron affinity. We're not really gonna jump into the trends. It's kind of the same idea when we are talking about ionization energy in comparison to why 2A and 3A are slightly different. And the reason is that when you're going from 2A or 1 to 2A, now you're adding an electron in the p orbital. And now you're going to have an empty orbital. So sometimes it's more difficult to add 1 to 2 than it is to 1, simply because in 2 your s orbital is completely full, where in 1 they want to fill that s orbital. So in 2 they don't want a stray electron sitting around in that p orbital, and in 1 they want a full s orbital. So you can kind of see the difference there. And the same thing can occur for 4A and 5A. 4A is willing to add an electron, because if you do the electron configuration for 4A here, you're going to have your p is going to be full, and then you're going to have one open orbital, so it's going to want to add. Whereas in 5A, your s orbital is full, and we already have our up, up, up. They're much happier with the up, up, up than trying to add that next down arrow in the 5A column. So there's kind of the exceptions with the trends in electron affinity. I know this was a very long presentation today. However, we've already talked about size of atoms, electron affinity, ionization energy last year. The difference is we just needed to go a little more in depth this year and talk about kind of the differences between the two and what are the exceptions to the rule.